Hey, everybody. It's March 23rd, 2022. It's the spring semester here at College of the Sequoias. This is Statistics, Introduction to Statistics. And we're in Chapter 9, which is on inferential statistics. Previously, we looked at the process of doing proportions and calculating, inferring something about the population proportion. And 9.2 is about estimating population mean. It's got to go. That's trying to knock my thing off. There we go. Estimating a population mean. And I wanted to remind you, since we're doing this sampling distribution thing, we need to get a mean and a standard deviation. Remember when we were doing proportion, we had the mean was p hat. And the standard deviation of p was square root of p times 1 minus p over n. We're aiming for something similar here. Just like we used the sample proportion to approximate the mean there, we're going to use the sample mean here, x bar, to approximate our population mean. And our standard deviation for the average, it's a fun formula. We want the standard deviation of the population, and we're going to divide it by the square root of n. Get on my page that I want. So this is what we want to be able to do what we were doing before. When we did proportions, we had everything we wanted. We were able to find a point estimate and we knew the sample. Here, we know we can calculate the sample mean pretty easy. X bar, and therefore our mean pretty easy. For standard deviation, we need the standard deviation of the population. But I can tell you something. If I know the standard deviation population, which I'm doing as a subscript of pop, I probably already know the mean too. Which means this is probably not going to work. So what can we do about this? Well, you're not going to test it on it, so I'm only going to just put little bullet points in here, the dude. Back in the 1900s, there's a dude named Gossett. And Gossett, he's working for Guinness Breweries. Guinness Brewery. And he needs to figure out, you know, how well certain beers, ales, whatever they were making at the time was working. And so he was doing a lot of tests, collecting a lot of samples, gathering a lot of data. And he ended up finding, he found a reasonable approximation, a good approximation to the standard deviation of the population. And it took a lot of work, and his employer wouldn't let him publish under his name. So he went and got a pseudonym, and he published under the name Student. That was the name he used. And so it's called Students. Oh, erase. It's called Students Distribution. And rather than using sigma, he chose to use T, not sigma. So it's called student's T distribution. Okay. And so the T distribution, it's a lot. It's a lot like the normal distribution with Z. You know, a good old Z-score, where we had a mean of 0 and standard deviation of 1. It's very similar to that. That looks funny. There's just a few minor differences. So let's just talk about what it does have. One, it's symmetric and bell-shaped. And God, I look away while I write for a second. It looks bad. Bell-shaped. And it's centered at mu equals 0. Bingo, matches up with Z-score. Now, something it is different about, and I'll change the color for things that are slightly different. It is different for different sample sizes. The T-score is different for different sample sizes. And then number 3, this is similar to the Z-score, or the normal distribution, since it is symmetrical about the mean. The area to the left of the center is the same as the area to the right of the center, which is 0.5. Also, the tails approach but never touch the number line. Which means it never equals 0. The number line is the 0 axis. Now, it might be 0.00000000000000001, but it's still not 0. But for all intents and purposes, it's effectively 0. Like the chances of it happening is like winning the lottery 12 times in a row at some point. It just gets that bad. Now, some more differences is the tails. Well, the center is a little shorter. Maybe I should say lower. And the tails are a little higher. Than Z. And I can actually show you that. While you're doing that, I will open up. That's not what I wanted. Where's my Zoom window? Where'd it go? The hell happened to it? Oh, I know what the problem is. I clicked to another tab. Okay, I was looking for the remote screen. Where'd it go? There it is. Okay. And I got it in pictures. I downloaded some today. I liked it. I thought they were really good. So we'll start with that one. And I'll open up that one on there too. So we'll look at that one in a second. This is the one we're looking at right now. You will notice that the Z distribution is this purple pinkish line. It's taller in the center, but as it goes outward, it dips below the blue line, which is the T distribution. How many times are you going to open that? Okay. So that's what I kind of meant. It's taller in the center. Oh, I said lower. Yeah, it is a little lower. The T distribution is a little lower than Z in the center, but a little higher than Z on when it goes towards the tails. And again, if I go too quick, let me know. What else? This is so effectively the height is different. It is worth noting as n increases, I write one word, I think another. As n increases, our sample deviation, recall we use S. S gets closer and closer to sigma of population. Closer to the standard deviation of the population. So this was pick 1. This is going to be pick 2. And degrees of freedom, I didn't mention this earlier, but the degree of DF, which means degrees of freedom, that is n-1. So keep that, we've seen that before. We've talked about that before. But that's what this DF is here. So like when n equals 2, the degrees of freedom is 1, and we've got this purple curve right here, which is the T distribution. The black one is the Z distribution. And notice as our degrees of freedom go up, n is going up. N is always 1 larger than this. So n is 4 here, n is 9 here, n is 21 here. Notice that this curve gets closer and closer to matching it in the center. And then at the tails get closer and closer to dropping down to what Z is down below. So as n gets larger, it gets approximately equal to our Z distribution. And so like, where's that value? This happens at about, S is approximately sigma when n is greater than or equal to 30. So that's actually going to be one of our checks. Remember, we had some checks. Our checks for proportion, we had n times p times 1 minus p was greater than or equal to 10. And n is less than or equal to 5% of the population. the checks for when we're doing mu, our population mean, we have two categories. A, if n is greater than or equal to 30, the curve is approximately normal and good to go. Now, where it changes, or where we got to actually do some work, I should say. If n is less than 30, we've got two things to check. We want to check the correlation statistic and see that it's greater than the critical value. And we just got done doing this in chapter 4, just like a week and a half ago. This is easy to look at on a QQ plot. And you click on add correlation statistic. And you might have to look up the critical value on that table in that handout. What we're going for here is that the QQ plot looks roughly like a line. Lines are straight, curves are bent. So we want a straight line, and I suppose it could go downward too. But as long as it's a line. And then if that one matches up, we got one more thing to check. That's not enough on its own. We want to check a box plot. And make sure there are no outliers. Okay. Let that give you a second to write that. Okay, so I told you that sigma is sigma population over the square root of n. Well, T is x bar minus mu over S divided by the square root of n. I know, right? Hell no. I don't want to do that by hand. Do you want to do that by hand? You got to calculate the mean. It's, oh, sorry, not x bar, x. Now I'm second guessing myself. It's got to be x bar. I'll look that up later. Totally second guessing myself. That sucks. I'm having a brain fart. We're not doing that. That's good news, right? Stack crunch, baby. Stack crunch. Stack crunch for the win. So to find T, we can do stats, calculators, T. And what you need for that is you need to know, you need the degrees of freedom. We'll look at that in a second. I just want to give you all your StatCrunch commands at once. And then when we're doing confidence intervals or hypothesis tests coming up in later chapters, we're going to go in StatCrunch, we're going to go stats, Tstats. And then you've got a menu of 3 things. I think there might be 4, that might have the power and width on here too. We got 1 sample, and that's chapter 11. We've got 2 sample and paired. And these 2 are both in chapter 12. All of our 1 sample tests are in chapter 11. 2 sample tests are in chapter 12, and 3 or more different groupings is chapter 13. Chapter 10 is when we start talking about hypothesis. So chapter 9, we're talking about confidence intervals. We'll tie in how these are connected, okay, when we get there. And those are our StatCrunch commands. Stats, calculators, Tstats, Tstats, choose a category. And then let's take a look at some of those. Actually, I've only got a little bit more to write down, so we may not be to the writing thing other than writing down what's on the homework. So let me just give you the last topic. We used to, like in the previous section, we had Z alpha, which was the area to the right of Z. T alpha is the same thing. And if one of the problems that I'm going to look at in our homework doesn't have that, I will simulate that. So let's look at some homework problems. I was going to take a look at 11, 15, 16, and 17. Does that sound like a good deal? I almost closed it that quickly. I'm going to open up StatCrunch real quick. That way I always have it open. That is not what I wanted to do. All right, so first question. A researcher wishes to estimate the proportion of adults who have high-speed internet access. What size sample should be obtained if she wishes the estimate to be within 0.02 with 95% confidence? If A, she uses a previous estimate of 0.28, and B, she does not use any prior estimates. So I'm going to click that back on text. Last time I had told you that we had the one of the options was power sample size. This is where we're going to take a look at it right now. I wanted to show that to you. So I'm going to move this back over to the left. And we're going to go stats, proportion stats. We've got one sample. And we're not doing with data or summary, we're doing power sample size. Power samples, oh, I didn't tell you this. You want to, let me move this out of the way. You want to click on, what is it called? Confidence interval width. Okay, and we're going to use stuff from there. And that's this box right here. Confidence interval width. The confidence level, we've got 4 boxes. We're going to enter 3 of them every single time. So it just depends on what 3 we have. It says 95% confidence, and I have the confidence level set at 0.95 as a default. That's what we want. This target proportion of 0.5, that is when there's no prior estimates. Let me add that over here in the writing. Damn it. When target proportion is 0.5, that means no prior estimates, which in our problem was part B. Okay. And you can see that right here, target proportion. God damn it, quit doing that. So can I scroll down? It says it wants the estimate to be within 0.02. So like if we have our number line and our proportions here, it wants 0.2 that way, or 0.02 that way. Well, the only 2 boxes I have left on this are width or sample size. And I am trying to calculate what size sample I should use. So I don't know that, which means I need width. And recall, width is twice that estimate margin of error. So the width is 2 times the 0.2, which is effectively just adding them together, is 0.04, which is what I will enter over here. So I got my confidence level. I got my width from this. It says the estimate to be within 0.02, which means either direction 0.02. That's where I got the width. And my previous estimate I need to put in for part A is right here, is 0.28. And I click compute. And notice that the first thing I want to point out is the width changed. It changed it to adjust to the sample size where it's a whole number, which means when I go into the next part, I'm going to have to change that. But it gave me the sample size and it rounded. And it looks like it might have rounded down, but let's check. Nope, it rounded the right way. So I got my sample size from that box right there. Part B, I need to reset my width back to 0.00 or actually, let's see if it changes. I'm going to do it with the width at point where it is and at 0.0. We need 0.5 as our target proportion because we don't have a prior estimate. And I'll click compute. And I get 2403. I'll put that over here real quick, just in case. But you really should reset the width. Look at that. I reset the width and it changed it. It says 2401. So let's see if it's going to take that 2403. Oh, it did. Shouldn't have. I guess it had a range of numbers it was willing to take. Should have been 2401. All right, let's take a look at, or is there any questions on that? Nope, okay. Let's take a look at number 15. An agricultural researcher, let me close this. An agricultural researcher is interested in estimating the mean length of the growing season in a region. I'm going to type these in. I know I can click on this box right here, but in order to keep the windows where they're both on the screen at the same time, I kind of needed to type them in. So I'm going to do that real quick. And then I'll read the question. See, make sure the numbers are right. 151, 158, 148, 141, 169, 192, 189, 184, 163, 146. Okay. An agricultural researcher is interested in estimating the mean length of the growing season in a region. Treating the last 10 years as a simple random sample, he obtains the following data, which represent the number of days of the growing season. So that's what these numbers are, the number of days that crops were growing. What is the point estimate of the population mean number of days of the growing season? So the population mean is about the same thing, number of days of growing. So we're looking for the mean of these, because remember, population mean is just X bar. And so we'll just do that. How do we calculate the mean? You guys have done this. You guys remember how? How do I do it in StatCrunch? Anybody? Oh, I got an answer. Yep. Not data, stats. Summary stats. You had the summary right. We don't use data for hardly anything. Data is mostly just for simulations and every once in a while sorting shit. Most everything's through stat. We go columns. And we got mean. Let's just grab the mean. Easy money. That's it. That's all I wanted. Wow, that's all I wanted. Holy cow. I thought that was a real problem. Look at me not doing the problem all the way through. All right, in a survey conducted by the Gallup organization, 1,100 adult Americans were asked. I'm going to move this over to the right since it's just text. 1,100 adult Americans were asked how many hours they worked in the previous week. Based on the results, a 95% confidence interval for the mean number of hours worked had a lower bound of 42.7 and an upper bound of 44.5. Provide 2 recommendations for decreasing the margin of error of the interval. So let me just, I kind of want to picture this. I got a number line. I don't know what my mean is in the middle, but I got 42.7 over there, and I've got 44.5 over here. Now this margin of error, remember the margin of error is related to that bell curve. And so 95% confidence interval is at like that plus or minus, it was 1.96 deviations. 2 when you use the empirical rule, but 1.96 when we start doing real calculations. And so if I can make my sigma smaller, oh, I'm going to make it pictorially smaller. Sigma to little sigma. That means going at like this is 1 deviation, 2 deviations, 1 deviation, 2 deviations. If I can make it smaller, it might only go out that far. And that would be 1 and 2 deviations. And I would have a smaller margin of error because the margin of error is the distance to that marker. So if I can increase the standard deviation or decrease the standard deviation, that should work. How do I do that though? I can't just change the numbers, okay? Standard deviation though, gets smaller as the sample size increases. So sigma goes down as n goes up. We saw that when we were doing those simulations. In fact, we can see it on this picture over here. Sigma is the height of this, or how far out this line is effectively. To get the same value, if we go down, it's further to the left. N goes up is good. So it should be as increasing the sample size should work. And it says pick 2. So what else do I got here? Oh, another way to do it would be like I chose 95%. If I wanted 99%, 99% would cover a bigger region. And 90% would cover a smaller region. So we could lower our confidence level, which isn't usually that desirable, but if you've only got so many options, you only got so many options. So decrease the confidence level and increase the sample size should be our two answers. That one takes a lot of reasoning and understanding about the stats, so I wanted to do it with you guys. It's not that intuitive. I see something in chat. Okay. Oh, that was probably a response to earlier. I ordered a green tea with lemonade yesterday from Starbucks. And they put green tea with lemonade with peach in there, and like more peach than like lemonade. And I am done ordering green tea with lemonade. I'm getting green tea with peach. This shit's phenomenal tasting. It's delicious. I strongly recommend you try peach tea. Oh, it's delicious. All right, that was number 16, and I wanted to go over number 17 with you, and we will be done. Unless I need to show you the T alpha. We'll see. Ooh, there's more going on here. Look at all this. Jones came at you with a big problem. A simple random sample of size n is drawn from a population that is normally distributed. The sample mean x is found to be 100. 101. I'm going to write this down on my data. X bar equals 101. And it says my sample standard deviation S is 12. And we're going to do a couple things. We're going to do the 98% confidence interval. So we got three values. I'm going to write these down because I think we're comparing them all at the end. So A is 98% confidence when N is 22. Then B is 98% confidence when N is 12. So like the sample size goes down, maybe they're going to ask what's the difference. And then we put, for C, we put N back up to 22, but instead we lower the confidence interval. So looks like, just like looking at it, we are checking the effect of lowering N, which is off screen because this window is too big. We're checking the effect of lowering N. And then also lowering our confidence interval. So we're going to set like a baseline here and see what happens with the other two. So that's what they're like trying to teach us something here. And I suspect it's related to the problem we just did. So let's just go about doing it. It's the stats, it's Tstats. I told you that's our new thing. That's our new thing for today. We've got one sample. We're going to go with one sample. We don't have data. They would have a pile of data like this over here. So we'll go with summary. And now notice they want three pieces of information. They want the sample mean, which is 101. The sample standard deviation, which is 12. And the sample size is 22. We're doing confidence intervals and we're starting at 98. Always, always, always check this when you're doing confidence interval. Check that you got the right size. It defaults to 95 because that's the most common one, but it isn't always the case. I click compute and they give me a lower bound of 94 to 1 decimal place is 94.6. And 107.4 is the upper bound. Y'all see that? All right, so I'm going to graph that on my number line. I'm going to make a little number line here because we're going to see how A, B, and C compare. And I've got my center is here. I don't know how I'll give some room for some movement. 94.6 is over here. 107.4 is over there. I know my mean is in the middle, and we already had that, which was 101. So this was A. Those values were part A. That's our baseline. All right, let's come over here and check B and C. B says redo this. So I'm going to go stats, summary stats, not summary stats, Tstats, one sample with summary. And I would normally just edit the other one, but I wanted to make sure you see a couple times. That is not 191, that's 101. And sample size is 12 here. And I need to reset the confidence interval to 98. Now I match, I got 98% and it's 12. And I get 91.6. And 110.4. Those are correct. And I'm going to come over here and mark those down. 91.6 is left of here. .6 is right there. My father-in-law's here. I think that's him. Doorbell ring. 91.6 is there. 110.4 is over here. So it looks like our change here was N went from 22 to 12. And so by lowering N, we increase the margin of error. Because the margin of error was initially that distance. That was our E for part A. But when we change it to 12, our margin of error is that long. Part B. So I imagine they're going to ask us about something about that. Let's just come and take a look. How does I was right, look at that. How does decreasing the sample size affect the margin of error? We can see that decreasing the sample size raises the margin of error, increases. So you can draw this out on a number line and just see what's happening. A lot of students just, for everyone that's not sitting in this lecture and that doesn't patiently wait through to the end to see these problems, is not, it's not intuitive. You gotta, it's like takes getting pointed out and looking at it a couple times. That's definitely what's happening now. Is N increased, the margin, or N decreased, the margin of error went up. And now we're going to do the same thing, but now our confidence level goes down. So I'll close those. those stats, Tstats, one sample with summary. I'm entering the same stuff. We got 101, we got 12. Sample size is back to 22. Confidence interval is 0.95, and that's what is the default, so I can leave that alone. And I'll click compute. And I get the lower limit is 95.7. I wish they used the same words. Isn't that fucking dirty? That's dirty. This homework program uses StatCrunch every time, and yet they call it lower bound here, and they call it lower limit over here. That's just designed to mislead students, if you ask me. I think that's pretty fucked up. And if I were writing this book, I would do something about, you know what? I know who writes this book. I'm going to tell them to change the word to match StatCrunch. I don't know if they'll listen to me, but I'm going to try. Did I do everything right? 95.7, 106.3. I'll check my answers. All right, they're going to want me to use that. So I'm going to come graph that and see what's going on. So I've got, for part C, I've got 95.7, which is a little larger than 94.6. And I've got 106.3, which is a little lower than 107.4. Which looks like our margin of error has gone down. It's shorter. So is that what they're asking us here? How does decreasing the level of confidence affect the margin of error? As the level of confidence decreased, so did the error. All right, let's see what D says. Should the confidence intervals in part A through C, could we have done it? Or should, I don't know, not could we have? Let me just read it as this. Should the confidence intervals in parts A through C have been computed if the population had not been normally distributed? Well, we wanted n greater than or equal to 30. And in none of these cases, n was greater than 30. So the other thing was that we wanted to check the QQ plot for the correlation statistic to see if it's approximately linear. And we wanted to check the box plot. And without the data, we can't do either of those. So we should say no, the population needs to be normally distributed. Since we can't do the check, we need that stuff. And that's it. You guys got any questions?
Could you go back up on the?
No, I don't got any question.
All right, let's get you out of guys out of here and ladies out of here an hour early. How about that?
Mr. Jones?
What?
I think Gabe has a question for you, Professor Jones.
Oh, what's up, Gabe?
Could you go back up on the notes? I didn't write everything down.
Yeah. How far back you want me to go?
Right, a little bit higher. A little bit higher. Right there.
All right, I'll start there, and then as you need it, let me know.
No, it's just this portion right here. I didn't get everything down.
Okay. Is there any other questions? If not, I'll stop the recording, and I'll leave this up while you do that.
No, I don't have any other questions.
All right.
No, I don't got any questions.
All right, then have a good day.